Thank you, sir. Thank you for your introduction. Welcome all participants to the webinar. Today we are going to discuss about the introduction to biomechanical simulation using OpenSim. So before I get into section, I would like to thank my adaptive department, Dr. Ramakrishnan sir and Dr. Nalavan sir, for giving me a wonderful opportunity to share my knowledge in this series of lecture. Okay, it's a time to get into the section. So before I get into the core of the section, I just want to share my views about National Biomechanics Day. It's a worldwide celebration by a biomechanics community. So actually, biomechanics is recognized as a breakthrough science of 21st century. So we have started celebrating this from 2017. After that, it's been really international. You can follow biomechanicsinitiative.org for getting a more information about a biomechanical day celebration. It's celebrated worldwide, and you'll be getting a lot of webinar section, hands-on experience. So a lot of initiatives have been done. So I request you all to get into the biomechanicalinitiative.org to gain a more uh, background about the National Biomechanics Day. Okay. Fine. So to build up a curiosity, right? So I just want to go up a Gene's 1998 movie. So Sankar, the first man, I guess, to simulate Aishwarya Rai's Bharatanatyam simulation in skeleton modeling. So we are going to do a similar kind of simulation today. So I hope this slide will build you a great curiosity among you people. So let's get into it. So before getting to the core concepts, so I want to just make you go aware that why we need a simulation in biomechanics. Okay, if you're doing any biomechanical analysis on a subject, okay, so probably we'll do some video analysis or you do some visual analysis qualitatively. Even definitely in quantitative analysis also in a video. But in a video we can't understand how the muscle organs performs in this movement and how the muscles have been activated. It's very tough to understand the anatomy technical and physiological part. But we are with this OpenSim simulation, we can understand that. So we can understand what the muscle activation and what is the force acting on the joints, and even what is the tendon length on this different movement of action. Yes, it's everything is possible. So I guess for us, biomechanics simulation, sky is the limit using OpenSim. So you can see the slide of fast bowlers was a running simulation. So where we are such a quantitative analysis of actually your muscles, we can see activating where the muscles have been activated on the different moment. So which help us to increase the performance, injury prevention, and lot on lot dimensional of core analysis is possible. So not only the qualitative, we can do some quantitative analysis also. So we need numbers to play in a research world. So as you can see, you can generate a lot of graphs. You can even integrate your experimental EMG data with the simulation as well as force plate data and 3D video recorded data. Yes, it's possible to integrate with your simulations. So if you can now today we are going to do some 3D camera data with our model, and we're going to simulate a gate cycle. So definitely we'll do something a great hands-on experience on qualitative and quantitative analysis. So before we get into the hands-on experiments, we wanted to make you all be aware and comfortable with what's OpenSim. OpenSim is a freely available software. So it's been developed by yeah, Stanford University. So it's we can do a lot of analysis. Okay, so now in the case of sports, we can do increase the performance analysis is possible, injury prevention. More than that, even a clinical biomechanics have been worked on this. Even robotics, computer science, so a lot and a lot. Okay, so even orthopedic surgical planning is also been done. And rehabilitation is also been possible in OpenSim. So I guess for me, you can say there's a lot of variety of dimensional. So biomechanics is an applied science, and in a sports area, so interdisciplinary and multidisciplinary way of approach is possible in OpenSim. So even if you take our example, where even OpenSim can be used in exercise physiology, yoga, physical education, sports coaching, even rather than not only a technology and biomechanics. So it becomes multidisciplinary, interdisciplinary approach is required to have a great output from OpenSim software. And most important thing is it's freely available, and it's you can even download the source code, and as well as the lot of musculoskeletal models are available and dynamic data are available, so you can easily take and practice it before you getting into a core research of your topic. Okay, so this is all about the OpenSim. So you can see in my slides. Sorry for the bad connectivity. Uh, okay. Now you can see how the opens global users in our worldwide. So you will take up in India. India is the second largest populated and highly growing economy. Still, I hope the OpenSim users are still not on an expected level. So I just want to make an awareness about OpenSim in this National Biomechanics Day 2022. So you can see what are the versatile they're using and the developed biomedical engineering, biophysics, and computational biomechanics was a lot and lot. Even you can be surprising you. Even robotics, the open sims are used. This computer science and neuroscience, and the open sims I mean widely used. You can see day year by year the users have been exponentially growing for an open sim. So I can say is open sim have a very good future and highly demanding. Skill for a biomechanist in future, not only biomechanist in excess physiology, also in yoga, and in versatile in lot of opportunities and job market is going to definitely going to develop in OpenSim. So today agenda, right? So I divided into two sections. So first section we are going to come across the basic of musculoskeletal modeling of lower extremity. So we'll do some model coordinates, muscles in a model, modeling limitations, and we'll generate some relationship between a joint angle, tendons length, and moment arms. Once we are done with that, we'll import motion data, 3D camera motion data with our musculoskeletal model, and we'll do some quantitative analysis of a gait cycle, and we'll compare our normal gait cycle of the CP patient, and we can do a normal with a large study with this. Okay, first we'll get into it. So it's a time for yeah, that's a OpenSim window. So to download a OpenSim, just type OpenSim in Google, and you will get an OpenSim website, community website. Just get into it, register yourself. You will receive an email with OpenSim download link probably in 24 hours. Just download it, and you can just normal installation. Once you're done, you'll have a shortcut, OpenSim shortcut in your desktop. Just click it up. You'll open up. You'll land up to this page. So I just want you to all to be a little familiar with your I mean software user interface. So in the on the top one, the was a toolbar, which where we will going to control our simulations. So in my left hand side, the first window is a navigator bar, where we will edit the properties of the muscles, and we will do some visualization of a muscle with the help of the navigator menu. So it's just like it will be like a tree and branch. It will be arranged in like a tree and branches. So in a coordinator, right, we'll control the degree of freedom of the model. So like moving the model and even just twisting up, turning around in x and y z axis. Everything has been a degree of freedom, and it's flexion, extension. So we will all be doing it in a coordinator below. So in my left and bottom side, and the big huge window is a visualizer window where you visualize all the simulations. So probably after this section, right, to bit more about OpenSim to be familiar and get practicing. So this is where you will get a welcome to OpenSim, right? So you're getting started. So you will have installation guide and how to contribute and what's new in 4.3. So this is a 4.3. So even you can have a lot of documentation about the theories of publication scripts. So these will help you up with understanding more deeper inside the OpenSim's background functions. Okay. So as a beginner and in OpenSim as well as in as a student in biomechanics, this example and tutorials definitely help you up. So introductory, intermediate, advanced. You ask, you say, I recommend you to start with the intermediate and do advanced. Once you complete all this exercise, you'll be definitely be extremely familiar, and you can even use OpenSim for your research. So forums will help you to update. If you have any questions, we can use forums to clarify it. Best practices. So there is a trouble in a simulation. Okay, so getting a simulation just as it is not definitely will never help you in a, so we need some best practices to get an accurate answers, so accurate results. So there are a lot of best practices. I mean will be there in this best practice. So if you click it, it'll lead you to the website. So we just recommend you to follow the best practices for different exercises, and general FAQs will be there. And you can even download a musculoskeleton different models, motion, simulation data, utilities and extensions. So it will be helpful to get a freely available 3D motion data, EMG data. So you'll be helpful to explore a lot. Okay, you don't need a EMG or 3D cameras to explore a lot in OpenSim. So you definitely, it's a really great learning tool. Okay, this is teaching apps definitely use you if you are an assistant professor or a professor in a university. These videos, courses, and teaching material will be really helpful for you to teach your students, and meanwhile to give up a lot of assignments based on OpenSim. Okay, okay. Without learning, we'll get into it. So I'll just open a file, open a model, and I'm just opening up. Okay, so you can see right. So we have done visualize a window loaded at a musculoskeletal model with a lower extremity. So where you can see right, there is no limbs in upper body as well as there is no muscles in upper body. So what actually is we are trying to do is we are limiting, we are making a lot of assumptions. Okay, so there is limitation in this model. So at present we are going to concentrate on a gauge cycle. So where only we are going to concentrate on lower extremity. So we don't need what is going to happen. We're not going to consider what's going to in upper body. So we are all going to consider what's going to happen in the lower part of your body. How your legs moves, how your ankle is moving. So how is going to happen in your knee. So what are the muscles are going to contribute on a gait cycle. So we're just going to concentrate on the lower part of the body. So we omitted the upper part. And second, a lot of assumption is we are just have the only bones and muscles which have been really contributing in the, so you can see there is between the knees the patella is missing, and there is even a limitation in the range of motion. Okay, in this model we can't move the toes flexion, toes extension cannot be done. So there are a lot of limitations. Okay, but that limitation should not affect the accuracy of our results. Definitely we're not going to get 100%. So if there is a limitation, so we are trying to get 100 percentage of a result, but with a lot of limitations. Why we need to be in a approximate our model is because first thing is we'll need very less computational power. If we need actually, if we want to simulate as it is in nature, right, we need a supercomputer definitely, because we have been demanding a long computational power. So computational power will definitely be reduced, and the size of the problem, I mean size of the computation, size of problem reduced, the computational power is reduced, the time consumption is reduced, so it's easy for you to analyze. So this is there is a limitation accuracy have been done in any simulation. Okay, so once we more, I want you to be a little familiar with the mouse control. So left key, right, I'm just now clicking my left hand side key in my mouse, which help me to rotate the screen. Okay, so I can see this left hand side of my mouse is help me to rotate the screen. My right hand key is help me to pan. So I'm just moving the screen my model, and zoom in and zoom in for central scrolling button of a mouse is being used. So you can see a lot of some buttons over there. So over here, right, it's on a front view. So I'm just giving a side view, so you can see my visualize. I mean, sorry, top view, side view, rear view, and the bottom view, and another side view. Zoom in, zoom out, and this is the fit to screen. So over here, right, I can snap a snapshot, I can record my simulation, and this will is giving me x and y z axis, axes, which is no need now, so I just clicking it out. So this is my the control in a visualizer window. Okay, now it's time to get into a navigator. So in a navigator, right, so in a navigator, right, there will be load again. You can see a plus symbols in the right. Even if you click the plus symbols, right, you'll get another branch. So now at present we are going to work on the forces. In your forces you will have another subdivision muscle. So I will click the muscle over here. So you can see all the muscle groups have been listed, over the body. So your here is around, I guess, around 92 muscles out there. So 42 per leg and 6 for the toes. So this model is approximately 1.8 meters height and with a mass of 75 kg. So however, right, so if you click all plus, so you can listing of all the muscles, all 92 muscles have been listed out. And if you want, you can even list it to be make you easier. So you can even list a group of muscle. For example, if I taking up a right knee extension, rectus femoris, vascular intermedius, lateral and medius. muscles have been listed inside a right hand side. So R reference point right hand side knee extension. Then in that group you can see all four muscles. Okay. So these are all about the, so over here we'll control the muscle. I mean, what are the muscles we need to view, and we can change the properties of the muscles. Everything will be done in the navigator. Okay, now it's a time to get into the coordinator window. So in coordinator you can see, right, you can see some scrolling. So you can scroll like scrolling, or okay. So we can whatever we do is we'll control the degree of freedom. So let's take pelvic tilt, right? So what it is, tilt the body in the z axis. You can see it's tilting up. So that's our control. So as you can see, the values are changing. These are the degrees. Okay, so this is in x axis, this is in y axis. Okay, so and even you can move in x, y, z. So I just go to pose, I give default. So once I give default, we'll come to the standing, I mean actual default position. Okay, so pose to default give you actual position. Even I can do hip flexion. Okay, so I just let's flexion and extension is possible. Okay, so there are, you can do a lot of range of motions over here. So this is possible. So what I do is, for an example, I'll do some another range of motions. So with that we can do some qualitative analysis. So before I'm doing a flexion, right? So I just want present, right? We are going to concentrate on our muscle. We'll concentrate on rectus femoris and vastus intermedius. So we are aware that that is under a group of. So I'm just working on the right hand side. So yeah, oh yeah. So I need only rectus femoris on my right hand side. So I give show only. You can see a rectus femoris muscle which connect is actually a biarticulary muscles which connect the hip and the knee joint. Okay, and I need a vastus intermedius muscle. I give show. So for that beginning I give show only to, I want to show the only this, and the next muscle, right, vastus I give show. So I need to observe these two muscles together. So what I do is I'm going to change the knee angle. Let's see what's going to happen. So it's coming down, it's getting extended. So the fiber length is keep on increasing, and at one point, right, it's wrapping around. Well, it's actually wrapping around the complete knee bottom. Okay, so I give pose default. What I do is I'm going to check the same thing in a 45 degree. So in a knee flexion, now I just change the knee flexion into 45 over here. So I'm going to change the knee angle. Okay, you can see, you can visualize that it's not wrapping completely around. Compared to the standing position, it's slightly lower, right? So the fiber length extension is changed in a 45 degree. If I change if I change over flexion or hip flexion 45, so just like in a positive direction, positive angle, it's just sliding down. So this is a, we have analyzed something in a qualitative way. So I need to save this pose, go to the pose and go to new, and you can save it up. Pose 45. Okay, now you go to pose, you give default, go to pose, give pose 45. So you can come to different poses in the simulation. Okay, now we'll do we'll plot some graph over. Okay, now we'll plot some graph. We'll go to tool and go to plot. In our y quantity, we are going to check up the fiber length. Okay, so we have to check what muscle fiber length we are going to plot. Okay, so in a muscle, right, so we are already aware that we are concentrating on a rectus femoris and vastus intermedius. So it's in a right knee extension. So I'm just clicking up the right femur and vastus intermedius, rectus femoris and vastus intermedius, and give close on x-axis, and we'll check the knee angle right. Okay, and just give add. Wow, cool. We got the graph now. So what the graph is getting is it gives you the value, the starting point of a fiber length at minus 120 until the 10. So we have been evidence that the rectus femoris has a higher fiber length compared to the vastus intermedius, but both have a same slope. Okay, so it's dropping gradually with the same difference. So that's something interesting over it. So now what I'm going to do is I'm going to change the pose, and we have been aware that we're going to get the pose to 45. So let me already record it, so I'll just make it a more pose 45. So in this pose, we are going to we're going to build up a same graph. So here also just I'm just editing to 45 and give add. Become something interesting. Okay, so you can see the rexus femoris is a red one, right, in a standing position, but you can see the green one, rexus femoris, in a green 45 degree. There is no change in vastus intermedius, but there is a change in the rectus femoris. In a 45 degree, it's dropped. The fiber length is dropped because it's a biarticulary muscle. I mean, two joint muscle which connects the hip and knee joint. So the fiber length is depends on both the joint. But in case of vastus intermedius, it connects only the knee joint. So it doesn't depend on the hip joint. So you can visualize that. Okay. So all I do is I just move the knee angle. You can see that. Okay. The fiber length is smaller in this pose. Let's go to default. Fiber length slightly longer comparatively. So it shows that it depends on the change in hip angle as well as the hip flexion. Okay, so we did a qualitative and quantitative analysis to understand the bioarticulatory muscles. So we can do a similar kind of study on. This is a really a great tool for teaching the students. Okay, so you can use OpenSim for having a better understanding about the anatomy of human factors. So we'll move to the next graph. So our next graph is to plot a graph between a momentum and knee angle. So in a y quantity, I'm going to check up the momentum. In a momentum, I'm going to put up a momentum on a different knee angle. So I'm just going to take a knee angle right. So now in a muscle group, I'm going to check the same kind of muscles, rectus femoris and vastus intermedius, and give close. X quantity, I'm going to check up the knee angle right and give app. So you can see the graph. Okay, so the vastus intermedius is having a higher momentum compared to the rectus femoris, but nearing to 85, the rectus femoris picking up logarithmically. So I mean a small change in a knee angle, the growth was higher. There's even a small growth which increased the momentum faster. Okay, but compared to vastus intermedius, rectus femoris having a large momentum while knee angles keep moving. So here difference is small, where it's too high, but the peak and again drops and it's having a peak probably near to the 0 and suddenly it drops once you cross the 0. So this is how we feel while putting a squat. Okay, so we will feel the momentum. So we feel the pain because of this momentum. Slowly keep increasing and it's coming up and just drops. So something really interesting graph. Okay, so you can do the similar kinds of momentum graph for not only for knee angle, for change in ankle angle, lumbar rotation. So lot and lot. Okay, just I will again check it out. Okay, when a y-axis go to the momentum, you can see the lot of variables are there. We can do it. Okay, even in the x-axis, order you can check any so in a pelvic movement, reflection, addictions, rotation. So you can check a lot of variables out there. So it help us the students as well as teachers to teach the students well, and we can you will get a very well understanding about it. So you can change the different pose. We can measure all the muscles behavior. So it's really amazing tool for visualizingly understanding your textbook contents of facts. Okay, so we'll move on to the next section. So at present, right, we have plotted two graphs. One graph is fiber length versus knee angle, and another graph is momentum versus knee angle. Now it's a time to upload our motion data. Okay, so let's do some colorful simulations. I'll just close this graph now, and I'll go to all. I need to visualize all the muscles. So I give show in a hall. So I'm going to visualize all muscles. So through file, I go to load motion and I'm going to load the motions. Okay. So just play. Wow. So we'll reduce the speed to understand the gate. So we see how the man walks. Okay, so this is known as gait cycle. We are working on a gait cycle of a human. Okay, so before I'm going deep into it, let's learn some basic about gait cycle. Okay, so sorry to be a little slow. Fine, got it. So gait cycle. So gait cycle is divided into two phases: stance phase and swing phase. Stand phase is we having a contact with the ground. Swing phase we don't have a contact on the ground. Okay, in a stance phase is first heels touch the ground and probably a load response will be there. And it's completely you will be on a ground. Your foot will be completely on the ground, and your heel will take off. Your toes will be on a contact, and after that toe will take off. And next we will go on to the swing phase. So from 0 to 60 percentage of the cycle is in a stance. After 60% is in a swing. So after that you will move forward and your tibia will be straight. Okay, your tibia will be vertical. After that you will be land with your heel. So these are the phases. So from load response, mid stance, terminal stance, and pre-swing, and initial swing, mid swing, and terminal. So these are the normal thing. Okay. So we'll do the same thing over here. So we'll be doing the same visualization. I mean, a qualitative analysis using video recording. But how is simulation, right? So simulation help us to understand how the muscle moves. Okay. Okay. So you can see all degree of freedom on a coordinator window, and even you can slow down how muscle expands. You can visualize it. Even you can concentrate on a set of muscles. Okay. So for example, for a moment, I'm just planning to concentrate on a arm strength. So in arm strength, I'm going to concentrate on a serpiginous muscle. Okay. Go to mass and show only. Wow. Okay. So now what we will do is first we'll open some range of motion. Okay, we'll plot a graph for a range of motion. I'll go to tool. We'll plot range of motion. So what I'm going to do is I plan to understand change in a knee angle for a gait cycle. Okay, so in a y-axis, go to a normal gait. So I'm going to pick up the knee angle right hand side and give OK. And now x-axis, I'm going to check a normal gait. So complete gait cycle. So in x-axis, I'm going to have a gait cycle. In y-axis, I'm going to have a knee angle for my right hand leg. Wow. Got. So not only knee angle, even you can work on ankle angle too. So what I do is I check the ankle angle right and give a block. You can see knee angle have a larger range of motion compared to the ankle angle. Okay, but the both are almost similar in their function. Okay, you can see similar. So even ankle angle have a greater angle compared to your knee angle in a gait cycle. So something interesting, right? So you can plot a similar graph for any range of motion. Okay, you can have this much range of motion for left and right hand side of your gate. Okay, cool. So we'll move to the next plot. Okay. So we are already we are I told that we are concentrating on arm strength. So to make up the problem too much interesting, what I do is I will include one more abnormal gate, a coach gate. Okay. So for that I need a one more model. So I just go and open a model. So I have import another model. Okay. This is a new model. So for this model, I'm going to upload a motion. Okay, so I've been done. So we'll see the gate cycle. Wow. You can see, right, in this coach gate is excess flexion is there. So that is important and problem. And there was a hypothesis that once we extend the arm string and especially a simultaneous muscle, okay, if we extend a simultaneous muscle through surgery, is that possible to increase, decrease the flexion and to make a gait normal? So these are the studies are going on. So what we can do is we can take a coach gauge data of a CP patients and we can do some simulation analysis and we come to the conclusion that is it arm string surgery which definitely help the coach gait patient to be lead them to the normal gait. Okay, so we'll work on that area. We'll go to forces, muscles. Okay. Wow. So even over here, I'm just concentrating on one muscle, 17 muscle. I'm just sitting on. Yeah, there. Display. Show. Okay. So for next, I need to synchronize both the motion, right? So what I'm going to do is I'm going to synchronize it. I'm just with the help of control. I select both the motion thing and motion data and give synchronize. And just keep playing. So what I do is we are visualizing it. So it's evident that by through our observation that you can the arm string is shorten. Okay, so we'll do some with the help of qualitative. We can't conclude much, so we'll do some quantitative analysis also. We'll plot a graph. Go to plot and a y-axis muscle tendon line. Now muscle. Okay. So it's we've been aware that so it's in a right hand side hip adduction, semiderian muscle, close, x-axis, alright, gait cycle. So it's a coach gait cycle. Oh, sorry, just a second. I need to load a normal gait cycle beginning. Just a second, no lock. No, it's not loaded. So I have to click the model. Okay, then we need to load the data. So x quantity, yeah, done. So muscle tendon length, now muscle. I'm going to check the semiderian muscle. So it's in a right hand side knee bending. So I just check in the name semiderian muscle. X-axis, normal gait, and give add. Okay, cool. So what we see is a normal gait for a normal gait cycle. So what we seen is how the semiderian muscle tendon length is varying for a gait from 0 to 100%. Okay, so here 0 is 0 and 1 is an 100%. So what I do is I will change this to normal and what I mean normal. So I'll delete this for better understanding. I just made it as a normal. What we do is we'll plot the patient's CP patient gait cycle. Okay. Yeah. Cool. We got it. Muscle tendon length and go to muscle. We know that it's in a bending, semiderian muscle. Give close and next candidate coach grip and give back. Cool. We got the graph. So what happened is actually the problem that excess flexion is happening here is because of the shortage we have seen the beginning itself in the zero itself, in the 0% of the gait cycle itself. You can see there is a shortage in a muscle tendon length. So once we increase the gaits, muscle tendon length through surgery to here, it will in and around it will follow the same pattern of lengthening throughout the gait cycle. So with the help of surgery, if we increase the tendon length, definitely the patient, this CP patient will get in and around a normal gait, the better improvement. So these are how the simulation is helping orthosurgeons to come up with the kinematics data to understand that is we need surgery or not. Okay, so similar way we can do a lot of analysis for injury preventions and also the performance increase in a sports. So we have done some basic analysis using a walking gait. Even we can work on running gait cycle or lot of possibilities are there, and it's one of the best tool to teach the students in basic anatomy and muscles groups, especially for beginners in biomechanics. I hope this section will be helpful for you people to understand beginning concepts and of the OpenSim. Is there any clarification? Anybody? Okay, fine. So we are in the end of the section. So we'll wind up now. Okay. So you can see a world of simulation. So the simulation is not only for human, but even we can do some animal biomechanics. You can, what you see is how the ostrich running. Okay, how tendons are, length is varying, the ostrich running. Even you can see a golfer. Okay, all the forces acting, all the forces acting. So we did a simulation on by making a golfer to hit the golf ball in a force plate. Okay, so even in this slide we will be seeing the range of motion of the tennis player. Okay, we have plotted the locus of the bat, how he hits, how the locus, and how even range of motions, and even the how the muscle, how the muscles have been activated. So these tools are done in OpenSim. Over here is a Bob. Okay, so Bob means biomechanics of bodies. It's been developed by a MATLAB. So the roller simulation is something really great, and you can understand the human factors and actual movement a lot with the help of this. So this very good qualitative and quantitative analysis can be done with the help of OpenSim and even as in through any simulation software. Okay, so another area of simulation, right? So over there, what we done is something using human factors, movements, ergonomics we have studied. Okay, so even we can do another area of biomechanical simulation is find element method (FEM). So here, right, the find element method is help us to understand the structure. Structure strength of the bone. Is it when the bone is going to fail and how much load is acting on a bone? So find element method is there FEM, and even another side computation fluid dynamics, understand the fluid dynamics of the human system. Okay, any biological system, how the blood flow inside a vein, how the heart function, especially on working on circulatory system. So there are huge other area also, probably for next year biomechanical day I will planning to take up some section on computation fluid dynamics, because that's my core area. Okay, CFD for biomedical simulation. So I'll definitely will look up this similar kind of section next year. Okay, so you can reach us for any updates or any help regarding a simulation or any consultancy through us. So you can reach my head of the department, Dr. Ramakrishnan sir, as well as Dr. Nalavan sir. To reach me anything for your any questions or any help regarding OpenSim or any other need to the sports aerodynamics or technology, you can reach me out. So my mails is on the slides. So thanks for attending the webinar. And one more time, I thank the Tamil Nadu Physical Education Sports University management and my department, head of the department, Dr. Ramakrishnan sir, and Dr. Nalavan sir for giving me this wonderful opportunity. Thanks for participating in this webinar. Thank you for all listeners. Thank you so much.